Hi everyone, my name's Kent. Today I'm here to talk to you about SMP virtual machines on verified kernel configurations. Last year at the seL4 Summit, I also talked about multiprocessing on seL4 using verified kernels, and this is somewhat of a sequel. So last year I talked about how more and more hardware platforms are shipping with multiple cores, and applications are requiring more computing power. However, the current state of seL4 restricts high assurance designs that require verified kernel to running on a single CPU. seL4 does have a multi-core configuration called the big lock or the SMP kernel. It presents a single system image with a single kernel providing access to all cores. It supports SMP style applications, and existing IPC mechanisms are able to work cross-core mostly transparently. However, it's unverified, and there's still reasonably big amount of work required until it can be verified, because it's an inherently concurrent verification project because of all of the shared state in the kernel. And so until it is verified, there isn't really a way for high assurance systems to use a kernel where they require a verified configuration, so it can't be deployed in critical applications. But that's all right, because last year we introduced a multi-kernel as an interim approach. So it's a fully separated kernel instance on each core with no concurrency in the kernel. That allows you to access multiple cores without requiring complete verification of concurrency mechanisms in the core, because there's no concurrency in the core. And that allows us to use verifiable or verified kernels a lot sooner, because it's just using partitioned versions of the current verified kernel. And then over time, we're able to extend the proofs to cover more and more SMP mechanisms on a more reliable, more small cadence incrementally. End of last year, I sort of finished with a few follow-ups of my talk. One of the things that I mentioned that I wanted to look into a bit more was multiple VMs running on multiple cores. That involves single core VMs, each running on a separate core. And we were successfully able to do that. But what happens when you want one VM to be able to access multiple cores? Which brings us to the topic of today's talk, which is usable virtual CPU count by kernel configuration against the actual Partition multi-kernels don't provide a single system image, which means that you have to specifically choose which core you're executing on, and cross-core operations have to be explicit. However, guest OSs that are able to efficiently utilize multiple cores, like an SMP system, can perform a lot better when they're given access to those additional cores, even though we still may not trust them to completely manage their system resources. So allowing a guest to access multiple cores is allowed and supported by the underlying hardware architecture. So we should expect to be able to do it using seL4, and we really want to be able to do it using verified configurations of seL4. So what does it look like potentially doing SMP guests on partitioned hosts? So here is a single core system where you have a single node, a single kernel running that node, running a single application, which is a VMM driver, and that driver is hosting a virtual machine environment that's running a single core VM. Now, if we want to have a second core in that VM, we obviously need to add a second physical core, because no one's going to run a multi-core VM on a single core system. But because of the partition model of seL4 and the partition multi-kernel, we have a separate seL4 instance running and managing the resources for that second core, which means it needs to have a second application running on top, a VMM driver as well, that has a separate address space and minimal sharing with the other VMM driver. But if we want to run a single guest, that means we have to have a single virtual machine environment for that guest to run in. So inside this environment, we want to be able to load something like an SMP Linux kernel that's able to efficiently use the multiple cores, which means you want to have minimal serialization and low overhead introduced by the hypervisor. And the bit that's a bit counterintuitive is that you have somewhat built-in isolation because of the partitioning of the kernels, but at the top level, you sort of need to be able to have sharing inherent within the operating system. And so the rest of this talk, we're sort of going to go over a little bit over SMP systems, what an SMP environment typically requires, what the guest kernel is going to use, And then we're going to talk a little bit about hypervisor extensions that the hardware provides to efficiently virtualize guest environments, and then finishing up with a design for supporting and implementing this on a partitioned multi-kernel system. So hopefully this next slide, I don't lose many people, but basically here's a simple SMP system using the AArch64 ARM architecture, 2 cores. The main piece in there is that there's 2 parallel execution units that they can execute instructions on data in parallel, largely in parallel. And then most of the rest of the stuff is just there to support them running efficiently. So the next thing we have is a memory hierarchy with an L1 cache on each core, a shared L2 cache, and then falling through down to the memory on the system bus. What's important to note about the caching hierarchy is that the hardware implements a cache coherency protocol so that the different execution units see a coherent view of memory as they execute. And in addition to that, the hardware provides cache maintenance instructions for the OS to be able to explicitly synchronize caches when it's doing things that are outside the realm of normal memory operations. On the ARMv8 architecture, there is the cache maintenance instructions have broadcast options where you can broadcast a maintenance operation across cores, so the guest is able to remotely manage cache, like remotely evict cache entries on other cores without having to send IPIs, and it's all just managed by the hardware. So that's one thing that's going to be hard to do in a partition system. Then we have the MMU, Memory Management Unit, which implements memory protection and address virtualization. There's always a separate MMU per core, otherwise you could only have one address space, and which means that you couldn't run multiple applications on separate cores in parallel. The MMU uses page tables to implement the address space translation, which sit in main memory, but then they're cached through the caching hierarchy. In addition, there's a TLB translation look-aside buffer cache that allows each MMU, like each address translation, to sort of not leave the core and do it quickly. But now this TLB cache also needs to be kept consistent with updates to the page tables, updates to address translations. And so there are also cache maintenance operations necessary to provided to be able to keep those caches synchronized with each other as the operating system changes address spaces. So think when the kernel is unmapping some region of executable memory on one core, it needs to make sure that the L1 instruction cache on the other core is invalidated. So that's like a TLB shootdown. Also something that's going to be hard to deal with in a partitioned multi-kernel system. Then there's a separate interrupt controller CPU interface on each core that's provided so that each core is able to independently prioritize, mask, acknowledge interrupts that are relevant for it. And a platform interrupt controller, or in this case the GIC, can direct platform interrupts to each core. And it also facilitates IPIs or software generated interrupts so each core can interrupt each other. And then hardware peripherals are largely global on the system bus. There are a few per processor or per core peripherals, like a platform timer, that each core sees its own set of registers to manage and program that timer. And then the last thing is synchronization requirements. So for each core, we need to make sure that they can agree on state and they can correctly implement mutual exclusion. And so the hardware provides mechanisms for memory ordering with synchronization barriers, atomic operations with the exclusive monitors and the load and store exclusive instructions, and optimizations for spin locks with the send event and wait for event signaling. And so that's most of the content for what you need in an SMP guest environment. So hold on to that. And now we're going to talk about what hypervisor extensions the hardware provides in order for a hypervisor to be able to support multiple guest operating systems, each running in their own virtualized physical SMP environment. So first up, we have an additional layer of page translations for the MMU. So this is known as the stage 2 address translation. So this creates an alternate physical address space for each guest, known as an internal physical address. But it's the main mechanism that the hardware can partition system resources from each guest so that guest A, the kernel in guest A, isn't able to access physical resources that the hypervisor doesn't want it to access. There's an additional set of page table entries in main memory to support this, the second stage of translation, and the TLBs in each MMU are sort of updated because they can potentially hold stage 2 translation entries, but they can also hold stage 1 plus stage 2 translation entries, so that for a single virtual address, the TLB contains a cached entry for the final physical address for that TLB entry. And it's tagged especially so that when you do VM switches or address space switches within a VM, you're not necessarily having to evict all of those entries in the cache for efficient switching. To support this, there's a new VM ID. So in non-hypervisor extensions, you have an address space ID, which is how a context switch can happen without the TLB having to be flushed. It also means that when you're doing operations that flush cache entries by virtual address, the address space ID is used to make sure that only the virtual addresses relevant to that particular tag are flushed. So now extending that to a hypervisor, the VM ID is like an ACID, like an address space ID, but for a hypervisor. And so when this is combined with the broadcast cache maintenance operations, so for example, in validating an instruction cache for this address space on all of the cores, the hardware has to know which guest you're referring to when the broadcast operation in the hardware reaches the other core. And so that's where the VMID is relevant. And the VMID is probably like we talked about partitioned state across a partitioned multi-core system, multi-kernel system. But in order for it to work, the VMIDs need to be globally managed. So if you have two guests, if you have one guest with two cores, the VMIDs for each of those cores needs to be the same. Otherwise, you'll get situations where cache invalidations will be invalidating caches for arbitrary guests. Otherwise, there's additional context state, there's additional hardware state for virtual interrupts using virtual CPU interfaces, additional system registers for allowing you to modify system registers that the guest sees, virtual timer registers for having virtual time. These are all largely dealt with on a per core basis. So you have an implementation for a single core VM. It's mostly the same for a multi-core VM with some extra details. And virtual devices are largely supported using stage 2 page faulting to trap and emulate instructions, or maybe the hardware will provide a set of virtualized hardware registers. So that's where you have hardware optimized virtual devices, where you can say pass through different parts of a device to guest, and then the device is aware of virtualization. So that's the background. How do we tie it all together in a partition? Like, how do we build a partitioned VMM on top of partitioned kernels? It's inherently going to be a distributed system where each side, like basically, if you think of there's a kernel thread or a kernel running in an event loop, a hypervisor has a thread, and the guest might have a vCPU thread. They're all tightly coupled onto this node. And likewise on this core, they're all tightly coupled onto this node. And so architecturally, there's no built-in synchronization or serialization. So when the guests are sort of running, and they're not trapping, they aren't needing to go across core. When they are trapping, they still don't need to go across core. And it's only when the hypervisors need to explicitly send messages across the core to do cross-core operations like a PSCI, which we'll get to, the cross-core serialization has to happen. And then down the bottom here is sort of the stage 2 physical memory, and the kernels, each kernel is isolating the memory that each application is able to access. And so just going across the bottom here quickly, like this is kernel 1 state. Kernel 1 is responsible for making sure that none of its processes are able to access its state, and it relies on kernel 2 to not access its state and to not let any of the other processes to access its state. The hypervisor 1 is able to access basically its private state, its shared state, and all of the guest state. And so there's kind of, its address space will basically give it access to this region of memory. And then it ensures, by programming the stage 2 translation tables, that guest 1 can only access this region of physical memory. Likewise, on the other side, it's kind of mirrored, where kernel has kernel state, but hypervisor 2 goes from this part of the hypervisor 2 private state up to the end of the shared state. And so each hypervisor instance isn't able to access by default the private state of each other hypervisor. And so it's sort of minimal sharing by default. And likewise, the guests are able to access the same memory, but they're not able to access kernel memory or other memory that aren't related to the guest. So that's mainly how the isolation is going to work. Where am I for time? So to communicate between the hypervisors, we need to have some way of sending messages between the hypervisors. Last year, we talked a little bit about communication. This is communication using async message passing. So each hypervisor is able to send messages into a circular queue and notify the other core. And the notification is facilitated by physical software-generated interrupts across cores that each of these hypervisors are able to receive using notification objects. And then they just have direct shared memory to be able to read the messages. And then the guests basically have one giant shared memory buffer that's their guest RAM. And it, of course, has to be mapped with the same VMID in the stage 2 translations. So what does this mean for regular operation? So basically, most of the time we want both cores to be running in the guest state, and we want to have minimal situations where we're trapping out of the guest or we're synchronizing or serializing on different cores. So for regular ISA operations, largely everything works as normal. Sorry. I forgot to bring some water. So yeah, regular ISA operations are largely the same. Memory operations work the same way. Transparently, a memory operation may cause a page fault and then, well, not a page fault, it will cause a TLB to miss in the cache, and then 2 levels of translations will translate that address into a physical address by going out to main memory and reading 2 sets of page tables and loading it all back in. This is all how the hardware virtualization extensions are supposed to be used. Regular process switching, when the regular process context switching happens in the same way, when the guest VM wants to change applications, it doesn't have to do anything. It just changes the address space ID, changes the stage 1 translation table pointers, and things work as normal. TLB shootdowns. So now when a guest wants to be able to invalidate TLB entries on another core, it uses the standard TLB shootdown mechanism, and that works transparently. The hardware is able to broadcast that mechanism onto the other core, and the VMIDs ensure that the right entries on the other core are correctly invalidated. It's the same with cache, L1 cache invalidation, and spin lock synchronization largely happens on physical memory. So when 2 cores are implementing critical mutual exclusion using a spin lock, they are spinning on regular memory, and they're potentially using the send event and the wait for event signals to wake each other up for optimized spin locks, and that's all, doesn't need any special handling. And that's pretty much most of the operations that a guest has. There is a bit of extra stuff, so I'll just quickly try to go through that. So how does initialization work? The hypervisor on each core is launched by the runtime system. They initialize all of the replicated state. They then both set up the stage 2 translation tables for the guest. The first hypervisor is responsible for setting up any global state that's needed to run the global connectors. Meanwhile, the second hypervisor blocks waiting for an event because its core isn't supposed to start yet. The hypervisor loads and launches the first guest core. It runs, and eventually it's like, I want to start another core. And so on ARM, there's the PSCI, which I forget what the acronym stands for, but it's an interface, a system interface for powering up and powering down other cores. And so it's the mechanism for launching, for turning on, turning off other cores at runtime. So it does a PSI operation, which is usually a system monitor call or an SMC call. This traps into the first hypervisor. The first hypervisor then uses a signal in the kernel to send a message to the other hypervisor. Meanwhile, the first guest's SMC call is completed, and so it's just waiting for interrupts, because it's now said, I've powered on the other core, I'm now waiting for that core to power on and message me back. So the other hypervisor receives this event from the first hypervisor saying that there was a PSCI power on request, so just a single word message, and it's able to launch the second guest. The second guest starts up, it does its thing, potentially sends SGIs to the first core or releases a lock for the first core, and then the first core is able to resume, and then they can run in parallel. How am I on time? Sure. The second thing is how does the virtual interrupt controller work? Because the virtual interrupt controller has a global interrupt controller that's got global configuration for handling things like shared peripheral interrupts. But then there are local interfaces for doing things with per processor interrupts, and then also for handling software-generated interrupts. So in this case, hypervisors are starting up again. They initialize the shared state. Guest 1 starts. Remember, hypervisor 2 is currently waiting for the second core to start. It probes the interrupt controller. It programs the distributor. The distributor, it's programming, enabling all of the interrupts or disabling all of the interrupts, whatever its policy is for how it sets up the interrupt controller. It then programs a secondary per-core redistributor for the interrupt controller, and it programs any per-processor interrupts. This is where it sets up the platform timers, gets all of its timer interrupts. This is all still happening on a single core. I guess quickly I'll just talk about the virtual timer, or like a per-core timer. Each core is going to have a platform interrupt, say a 10 millisecond or 100 microsecond interrupt that gives it tick events, and this all happens largely through injecting per processor interrupts, and it just stays on that single core. It does trap into the kernel, trap into the hypervisor, inject, and all of that like a regular system, but it's not having to go across core. Eventually the second core wakes up, it programs its own redistributor, but there's sort of global state in this interrupt controller now. It programs its own PPIs, and now it wants to send an SGI, a software generated interrupt, or in x86 parlance, it's an IPI, an interprocessor interrupt. Shit. I'm so close. And as it's sending the SGI, I'm cursed. If I hold my screen up. Yeah, so it's basically pretend that there's a blue box here. But basically to send a software generated interrupt, the second guest traps, the hypervisor receives that trap, sees that a SGI was requested. It uses message parsing to parse that message over to the target core, which receives an interrupt using the kernel interrupt mechanisms. That hypervisor then injects the SGI into the other vCPU's interrupt controller, and it's able to receive the interrupt, and they continue happily executing. Unfortunately, I had one more interesting slide. So yeah, there are a few more examples which I won't necessarily go into, but feel free to ask me later or in questions if there's still time for questions. But it's things like, how do you deal with virtual devices? So like a VirtIO net, different cores within the same VM instance have potentially have single devices that they need to access to. So how do the hypervisors need to be able to have some form of synchronization to implement a shared device like that? Likewise with just regular cross-platform communication so that the VMs can communicate with other applications outside of the VM environment on the rest of the system, and other things for like privileged operations like SMC calls or protected device access, where you want to potentially provide access to some registers of a device, but you want to make sure that the contents of the reads and the writes are following a valid protocol. So that's kind of, like I've talked about a design, and as of a few days ago, it does actually work. And all this is just a fairly sophisticated IMX8 platform booting up with 2 cores, a bunch of device pass-through, the Debian system booting to login, doing its stuff. You'll see some interrupts come up somewhere. A whole bunch of IPIs being successfully communicated. And then finally, a pair of processes. So yeah, thanks for coming to my talk. Sorry for the AV issues.
Any questions?
So basically, you have the partition kernel, but in terms of hypervisor, it's SMP hypervisor. So how does it help the verification?
So it's actually the hypervisor is, I'd say it's potentially a partitioned hypervisor. It's able to use, because it has its own private state that the other core of the hypervisor cannot access. And the message parsing can be implemented using platform mechanisms so that the concurrency is still in a limited parts of the code. But for the same reason that you can't have concurrency in the kernel if you want to have a verified kernel, you couldn't verify a user level hypervisor for the same reasons. But you're still able to partition that hypervisor from the rest of the system. And so it's kind of leaving it for the engineering that's building that particular part of the system to implement the hypervisor in a way that they're comfortable with. But some of the design principles around having async message parsing and limited shared state means that you can do it in a largely independent way with limited concurrency.
Can you talk about what kinds of modifications you had to make to the seL4 kernel to enable this? For example, sending SGIs from user space. What was the scope of those modifications?
I can't even remember by now. So there were mostly modifications made for last year's talk. The biggest one is an invocation for sending an SGI. So the interrupt controller control capability has a additional invocation for creating a capability that's allowed to invoke a SGI for a particular target core with a particular interrupt ID. That's within the scope of what's verifiable today. There currently isn't a good built-in kernel mechanism for controlling or explicitly specifying what address space identifier gets used. So the VMID largely is controlled to be the same on each core by creating the address spaces in the same way, in the same ordering. So there is a modification that probably could be added to improve the usability there. And what else? There's a little bit of modification needed for one of the things I didn't talk about was when a guest wants to retarget a SPI, a physical shared peripheral interrupt from one core to the other core, the physical interrupt controller needs to have that remapped. A lot of platforms push a lot of that interrupt control into the secure monitor mode already. And so you can kind of use SMC calls to do it. But otherwise, notionally, the kernel's model for interrupt capabilities and interrupt handling largely all works on the local CPU interface. And so you could also break up the control for setting the target of a shared peripheral interrupt at the distributor level and sort of carve that out into a separate set of invocations and allow the kernel to program them. Because there isn't anything there that can break the kernel from working, because the kernel largely depends the kernel should only depend on per processor interrupts.
There are more questions, but unfortunately I think we're out of time. Sorry about that. Let's thank Kent.